In section 4.3, we're going to talk about Rolle's theorem and the mean-value theorem. Those theorems talk about if you have a function f on a, let's say it's a closed and bounded interval, these theorems will talk about a particular value of a derivative at a point somewhere within the domain. Before we discuss those, though, we need to talk about what it means to be a relative minimum or a relative maximum of a function. So let's let f be defined in the domain capital D and into the reals. A point x naught in the domain is a relative maximum, this is a double definition, or a relative minimum if for some epsilon greater than 0, the value of the function at x naught is greater than or equal to f of x for all x in the epsilon neighborhood around x naught. And it's a minimum if the value of the function at x naught is less than or equal to f of x for all x in the neighborhood. Now let's remind ourselves what this means here. I'll put it in parentheses. Well, the D is just in the domain, so it means for all x in the domain and also in this epsilon neighborhood of x naught. All this capital N neighborhood is x minus epsilon to x plus epsilon, like that. Okay, so you're probably familiar with relative minimum and relative maximum, but I'm going to do a couple of examples where it might be different than what you remember in calculus. Let's take the function f of x equals x squared on the domain just -1 to 2. So I've got a graph here from -1 to 2. Well, a good relative minimum would be at 0. If you move to the right of 0 or to the left of 0, the value of the function is increasing in both directions. So that would be a relative minimum. Maybe I'll write relative minimum at x equals 0. And the value of the function at that height happens to be 0 as well. But at the end points of these domain, in both cases, I have a relative maximum. If you are on this point, if you're from this point, if you look from 2 plus or minus any numbers, if you're in the domain, you're decreasing as you leave, as you move away from 2. Now there are no numbers in the domain to the right of 2, so you're only going in one direction. And you usually think of a relative maximum as having a tangent line that's horizontal to the graph. In this case, you don't get that. And it's only because we're at the end of the domain of a closed bounded interval. And the same thing over here. At -1, we also have a relative maximum. At x equals 2 and x equals -1, we have a relative maximum. And similarly, if we took the graph of f of x equals x cubed, or consider that function on 0 to 1 only, I kind of drew it from -1 to 1, just dotted over here, but all we're talking about is this part right here. Well, I would have a relative maximum at x equals 1, and the value of the function looks like it would be the height of 1. And there's a relative minimum at x equals 0. So it is not simply the case that you can only have a relative minimum or a relative maximum of a function where the tangent line to a point is a horizontal line. We normally think, again, consider maybe the sine curve, where it has an infinite number of relative maxima, and at each one of them, you would have a horizontal line touching the graph there, and relative minimum at all these valley points as well, and the horizontal line there as well. So this is kind of the cases where you do not have a derivative defined, where you have a horizontal tangent line at the relative minimum or maximum, in this example or in this example. Now, at least in this example, and actually in this example as well, the since the domain is 0 to 1, this would have a horizontal line at x equals 0. And this one also has a horizontal line, a tangent line at x equals 0.